Hello, everyone. Welcome to Sleep Space. Tonight, we will talk about why everything you can see, touch, and even imagine, is made of atoms. Whether you're lying in bed, gently preparing to rest, or simply enjoying the quiet of the evening, I invite you to relax as we slowly drift into the deep science of what makes up the universe. This journey begins with something incredibly small, yet unimaginably important: the atom. At first glance, the world appears solid and continuous. We see objects, colours, textures. We feel warmth or cold, soft or hard. But beneath all those sensations, underneath everything we perceive, is something far more fundamental: a tiny, invisible structure that acts as the building block of all matter. That building block is the atom. So, what exactly is an atom? The word atom comes from the Greek word atomos, which means uncuttable or indivisible. It was first suggested over 2,000 years ago by the philosopher Democritus, who imagined that if you kept dividing a piece of matter into smaller and smaller pieces, eventually you'd reach something that could not be divided any further. He believed these tiny, eternal units made up all matter in the universe. Of course, Democritus had no way of proving this. It was pure philosophy, and for centuries the idea of atoms remained just that: an idea. It wasn't until the scientific revolution, thousands of years later, that evidence began to accumulate. Today, with the help of incredibly sensitive instruments and techniques, we know atoms not only exist, but that they are the foundation of everything. Atoms are incredibly small, so small, in fact, that a single grain of sand contains more atoms than there are stars in the observable universe. If you were to line up atoms side by side, it would take about 100 million of them to span just 1 centimetre. Despite their tiny size, atoms are complex and structured. Each one has a dense centre called the nucleus. This nucleus contains two types of subatomic particles: protons and neutrons. Surrounding the nucleus are electrons, tiny negatively charged particles that move rapidly in clouds or shells. Though these electrons are often shown in textbooks as orbiting in neat paths, their actual behavior is governed by the strange rules of quantum mechanics, which means we can only predict the probability of where they might be. Now, you might wonder, if atoms are mostly empty space, how can anything feel solid? That's a wonderful question, and it brings us to one of the most fascinating truths in physics. Matter is not solid in the way we think it is. The reason things feel solid is not because atoms are packed tightly together like marbles in a jar, but because of the electromagnetic forces between their electrons. When your hand touches a table, what you're really feeling is the repulsion between the outer electron clouds of the atoms in your skin and the atoms in the table. They never actually touch in the way we think of contact. It's more like an invisible force pushing back, creating the sensation of pressure or solidity. But why atoms? Why not some other kind of building block? The answer lies in the way the universe is organized. The atom is a product of natural stability. If we go back to the earliest moments after the Big Bang, the universe was a hot, dense soup of fundamental particles. Over time, as things cooled, these particles began to combine. Protons and neutrons formed from even smaller components called quarks. Electrons remained as individual particles. Eventually, protons and neutrons clumped together to form atomic nuclei, and when the universe cooled enough, electrons were captured around these nuclei, forming the first atoms, mostly hydrogen, the simplest atom of all. The reason atoms work so well as building blocks is because of their stability. The electromagnetic force holds electrons in place around the nucleus, while the strong nuclear force binds protons and neutrons together inside it. These forces act in perfect balance, allowing atoms to exist for billions of years without falling apart. As time went on, in stars like our Sun, nuclear fusion created heavier atoms by forcing smaller ones together under immense heat and pressure. Helium, carbon, oxygen, iron, these were born in the hearts of stars. When those stars exploded as supernovae, they scattered these atoms across the universe, seeding the material for planets, moons, oceans, trees, and eventually us. Every part of you, your bones, your blood, your thoughts, are made of atoms that were forged in the bellies of ancient stars. These atoms combine in endless ways to form molecules, and those molecules form everything else, from water and air to DNA and plastic, from the bark of a tree to the circuits in your phone. It's all atoms, even things we think of as empty, like the space between the planets or the silence between words, are filled with atoms, or at least fields that influence them. Now, one of the beautiful things about atoms is their modularity. Like a set of cosmic Lego bricks, there are just over 100 different types of atoms, called elements, found in the periodic table. Each element is defined by the number of protons in its nucleus. Hydrogen has 1, helium has 2, carbon has 6, oxygen has 8. These numbers determine an atom's identity and its chemical behavior. But from this relatively small set of atomic types, the universe constructs an infinite variety of structures. Atoms bond together by sharing or exchanging electrons, creating molecules. These molecules can be simple, like oxygen gas made of 2 oxygen atoms, or incredibly complex, like the proteins and enzymes that drive life itself. So why not something other than atoms? It turns out that atoms sit at a kind of sweet spot in the structure of matter. They're small enough to be governed by the rules of quantum mechanics, but large and stable enough to assemble into bigger things. If atoms were less stable, everything would fall apart. If the forces that hold them together were weaker or stronger by even a small amount, chemistry, and therefore life, might not be possible. In this sense, atoms are not just convenient, they're essential. They are the perfect compromise between the chaos of the quantum world and the order of the macroscopic world we live in. We've explored atoms in labs through electron microscopes and particle accelerators. We've even learned how to split them, releasing enormous amounts of energy in the process, both for power and, tragically, for weapons. Yet, despite all we've learned, atoms remain deeply mysterious. Their behavior, especially that of their electrons, defies classical logic and instead follows the odd yet consistent rules of quantum theory. The deeper we look, the more we realize the atom is not the end of the story, but a kind of middle layer. Beneath it are quarks and gluons. Above it are molecules, cells, and galaxies. But atoms are where it all comes together, where the rules of the very small meet the patterns of the very large. Even time and temperature, sound and colour, all of these depend on the arrangement and movement of atoms. Temperature, for instance, is just a measure of how fast atoms are moving. Sound is the vibration of atoms through a medium like air or water. Colour arises from the way atoms absorb and emit light. Everything you experience is, in a sense, a song sung by atoms. And in the quiet of this moment, as you breathe gently and your thoughts slow, consider that even your breath is a cloud of atoms, oxygen and nitrogen flowing in, carbon dioxide flowing out. These tiny particles are both utterly ordinary and deeply sacred. They connect you to the air, to the earth, to the stars. Every breath you take is made of ancient atoms that have passed through oceans, forests, and even other living beings. Atoms are not just what everything is made of. They are the story of how everything came to be. They are the universal building blocks of form, structure, sensation, and thought. And tonight, we begin our journey through their hidden world, one quiet moment at a time. When we speak of atoms as the foundation of everything, we must also appreciate the rich complexity hidden within their simplicity. Each atom, though unimaginably small, is a miniature universe unto itself, a delicate balance of forces, energy, and potential. To understand why everything is made of atoms, we must examine what they are made of, how they interact, and why they endure. An atom, at its heart, consists of three types of particles: protons, neutrons, and electrons. These particles are not equal in mass or charge, but they are all essential. The protons and neutrons reside in the nucleus, the dense central region of the atom, while the electrons form a kind of shifting cloud around that nucleus. These clouds define the atom's boundaries, even though they are mostly empty space. Let's begin with the nucleus. Protons are positively charged particles, and each carries exactly 1 unit of positive electric charge. Neutrons, on the other hand, have no electric charge. They are neutral. These two types of particles are remarkably similar in size and mass, and they are both composed of even smaller entities called quarks. Protons are made of 2 up quarks and 1 down quark, while neutrons consist of 2 down quarks and 1 up. Quarks themselves are held together by the strong nuclear force, one of the 4 fundamental forces of nature. This strong force is incredibly powerful, but it acts only over very short distances, less than the width of a proton. It's this force that binds protons and neutrons together inside the nucleus, overcoming the natural repulsion between the positively charged protons. Without it, atomic nuclei could not exist. This balance between attraction and repulsion creates the stability that allows atoms to persist. Electrons, though much lighter than protons or neutrons, play an equally important role. They carry a single negative charge, and they are attracted to the positive protons in the nucleus. But unlike planets orbiting a star, electrons do not travel in fixed orbits. Their behavior is dictated by quantum mechanics, and they exist in regions called orbitals, which describe the probabilities of finding an electron in a particular space around the nucleus. These orbitals come in different shapes and energies, and they determine how atoms interact with one another. What's fascinating is that the electron cloud gives an atom its size, while the nucleus gives it its mass. The nucleus is about 100,000 times smaller than the overall atom, yet it contains almost all of the atom's mass. To put it another way, if an atom were the size of a football stadium, the nucleus would be a marble at the center, and the electrons would be buzzing around the stands. But despite their minuscule size, atoms have a structure that leads to incredible variety. The number of protons in an atom's nucleus determines what element it is. 1 proton means hydrogen, 2 protons make helium, 6 protons, carbon, 8, oxygen. With each additional proton, the atom becomes a different element with distinct properties. This is why the periodic table is organized by atomic number. It reflects the number of protons in each element's atoms. Neutrons add another layer of complexity. Atoms of the same element can have different numbers of neutrons. These are called isotopes. For example, most carbon atoms have 6 neutrons, but some have 7 or 8. These variants behave almost identically in chemical reactions, but they may differ in mass and stability. Some isotopes are radioactive, meaning their nuclei are unstable and decay over time, releasing energy in the form of radiation. Electrons, meanwhile, determine an atom's chemistry. The way electrons are arranged in orbitals around the nucleus defines how atoms bond with one another. Atoms tend to seek stability, often by filling or emptying their outermost electron shells. This is what drives chemical reactions. Atoms sharing, donating, or accepting electrons in order to achieve stable configurations. When atoms come together, they form molecules. And it is in molecules that we begin to see the emergence of complexity. 2 hydrogen atoms and 1 oxygen atom make water. Carbon, hydrogen, and oxygen form sugars, fats, and alcohols. The same elements, arranged differently, produce wildly different substances. A change in how just a few atoms are connected can turn something nourishing into something poisonous. This modular nature of atoms and their bonds is why chemistry is sometimes called the central science. It bridges physics and biology. It explains why wood burns, why salt dissolves in water, why metals conduct electricity, and why the smell of a rose is different from that of gasoline. But atoms are not just useful for constructing matter, they are also the keepers of time. The most accurate clocks in the world, atomic clocks, rely on the vibrations of atoms, specifically the oscillations of electrons in cesium atoms. These oscillations are so regular and predictable that they define the international standard for a second. This means that even our concept of time is tied to the behavior of atoms. Atoms also help us understand energy. The electrons in an atom occupy different energy levels. When an atom absorbs energy, say from heat or light, its electrons can jump to higher energy levels. When they fall back down, they release energy in the form of photons, which we perceive as light. This is how neon signs glow, how stars shine, and how your phone screen emits color. The colors we see in the world, in fact, arise from atoms interacting with light. Each element absorbs and emits light at specific wavelengths. This unique signature is called an atomic spectrum, and it allows scientists to determine the composition of distant stars and galaxies. Even though we may never travel to those places, we can know what they are made of, simply by analyzing the light they send us. And yet, for all their significance, atoms are incredibly persistent. Most of the atoms in your body are billions of years old. The hydrogen in your cells was formed in the Big Bang. The calcium in your bones was forged in dying stars. The oxygen you breathe was created in the fusion cores of red giants. Atoms do not wear out or grow tired. They are passed along, recycled, repurposed. The atoms in your hand could have once been part of a mountain, a tree, or another living creature. This continuity is part of what makes atoms so fascinating. They are timeless travelers, wandering through the universe, assembling and reassembling into countless forms. Their journey is our journey. The matter that makes up your brain, the atoms that allow you to think, dream, and feel, was once dispersed in clouds of gas and dust across the cosmos. The structure of atoms also helps explain the properties of materials. Why is diamond hard but graphite soft, even though both are made of carbon? The answer lies in how the carbon atoms are arranged. In diamond, each carbon atom forms strong bonds with 4 others in a rigid, 3-dimensional lattice. In graphite, the atoms form flat layers that can slide past each other easily. Same atoms, different structure, entirely different properties. Metals, like copper and gold, have a different atomic arrangement. Their atoms are packed closely together in a crystalline lattice, with some electrons free to move. These free electrons allow metals to conduct electricity and heat. It's why wires are made of copper and are not of plastic. Plastics, in contrast, are made of long chains of atoms called polymers. These chains are flexible and lightweight, making plastics useful for all sorts of applications. The properties of a material, its strength, flexibility, color, conductivity, all come from the behavior of its atoms and how they are bonded. Even life itself is an emergent property of atoms. DNA, the blueprint of all known life, is a molecule made from atoms of carbon, hydrogen, nitrogen, oxygen, and phosphorus. The sequence of these atoms encodes information that guides the development and function of living organisms. Proteins, which carry out the tasks of life, are made by stringing together amino acids, each composed of atoms in precise arrangements. And so we find that atoms are not only the building blocks of matter, but also the carriers of information, energy, and time. They are both particle and wave, both stable and dynamic. They connect the world of stars to the world of cells. It is remarkable that something so small, so seemingly simple, can give rise to all the complexity and beauty we observe. From the dance of molecules in a snowflake to the fire in a volcano, from the rust on iron to the breath of a newborn, atoms are at work, quietly, invisibly, reliably. The more we learn about atoms, the more we realize how deeply they are woven into the fabric of everything. They are not just parts of matter, they are matter. They are the story of existence told in the language of the very small. And that story is just beginning. To truly grasp why atoms are the fundamental units of matter, we must understand how they behave, not just alone, but in relation to one another. Atoms are not isolated entities. They prefer to interact, to bond, to combine, and reorganize. In doing so, they create everything from gases in the atmosphere to the tissues of living beings. Their behavior is dictated by the laws of quantum mechanics, a realm where probability replaces certainty and where particles can act like waves. Let's take a closer look at how atoms connect. The most basic way atoms interact is through chemical bonds, and there are several types. The first is the covalent bond, where atoms share one or more pairs of electrons. This sharing allows each atom to achieve a more stable electronic configuration, often resembling that of noble gases like helium or neon. Water is a simple and beautiful example of covalent bonding. One oxygen atom shares electrons with two hydrogen atoms, forming a stable, bent molecule that has remarkable properties, like being less dense as a solid than a liquid. Then there are ionic bonds, where one atom donates an electron to another, resulting in positively and negatively charged ions that attract each other. Table salt, or sodium chloride, is formed this way. Sodium gives up an electron to chlorine, becoming a positively charged sodium ion. Chlorine, now with an extra electron, becomes negatively charged. The resulting attraction between oppositely charged ions forms a solid crystal. Another kind of interaction is the metallic bond, which occurs in metals. In this case, atoms release some of their electrons to form a shared sea of electrons. These electrons are free to move throughout the structure, which explains why metals conduct electricity and heat so well. The atoms remain in fixed positions, but the electrons flow, giving metals their characteristic luster and malleability. There are also van der Waals forces and hydrogen bonds, weaker interactions that play essential roles in biology. These forces help hold DNA strands together and allow water molecules to stick to each other and to surfaces. Though weak individually, these bonds become powerful when many act together. So atoms, through a variety of bonding methods, build molecules, which in turn form the materials and substances we experience in the physical world. These combinations are not random. They follow strict rules defined by electron configuration, energy levels, and quantum interactions. Let's pause here and appreciate just how ordered the universe is at the atomic level. Consider the carbon atom, for instance. Carbon has 4 electrons in its outer shell, which allows it to form up to 4 covalent bonds with other atoms. This simple feature gives carbon an extraordinary ability to form complex structures. Chains, rings, branches, and even three-dimensional networks. Carbon is the backbone of organic chemistry and the element upon which all known life is built. In fact, the very definition of organic refers to molecules containing carbon. Proteins, carbohydrates, lipids, nucleic acids, all the fundamental components of cells are made from carbon-based molecules. And yet, the variety is nearly endless. A slight change in the arrangement of atoms can transform one molecule into something entirely different. The same set of atoms, rearranged, can turn a medicine into a poison. This is the power of atoms, flexibility within stability. Atoms obey the rules of physics, but those rules allow for immense creativity in how atoms are combined. The result is the richness of material forms, from the crystalline beauty of quartz to the fluid complexity of blood plasma. But let's not forget about the quantum realm, the arena where atoms truly come to life. In the quantum world, particles like electrons behave in ways that defy everyday logic. They can exist in multiple states at once. They don't have exact positions or velocities. Instead, we describe them with probabilities, wave functions that tell us where the particle is likely to be found. This means that even the shape of an atom is a matter of probability. The electron cloud surrounding a nucleus isn't a solid object, but a region where an electron might be found. These clouds have distinct shapes: spheres, dumbbells, rings, depending on the energy level and the orbital type. These shapes influence how atoms bond and interact, giving rise to the structure of molecules. It's a strange and beautiful system. The very fuzziness of electrons, this probabilistic smearing of their position, is what allows for chemical bonding to occur in the first place. If electrons behaved like tiny marbles, rigid and fixed, atoms wouldn't combine so flexibly. The quantum behavior of subatomic particles makes the molecular world possible. Even more fascinating is the idea of quantum tunneling. Sometimes particles can tunnel through barriers that should be impenetrable, based on classical physics. This is not just a theoretical curiosity. It plays a vital role in processes like nuclear fusion in stars, where protons overcome their mutual repulsion to combine into helium and release energy. Without tunneling, the sun wouldn't shine. Quantum effects also help explain the behavior of atoms at very low temperatures. In a state known as a Bose-Einstein condensate, atoms can lose their individual identities and behave as a single, unified quantum entity. This is a state of matter that defies classical description and shows us that even atoms, stable, individual building blocks, can behave in radically new ways under the right conditions. Let's also touch on entanglement, a quantum phenomenon where particles become linked in such a way that the state of one instantly influences the state of another, even if they are far apart. While this is more common in photons and other elementary particles, atoms can also be entangled. Scientists have used entangled atoms to explore quantum communication and precision measurement. It's another way atoms demonstrate that they are more than just static units. They're dynamic participants in the strange and subtle universe. But not all atoms are created equal. Some are more reactive than others. The noble gases, helium, neon, argon, are known for their reluctance to bond. Their outer electron shells are full, making them chemically stable. On the other end of the spectrum are highly reactive elements like fluorine and sodium. Their electron configurations make them eager to bond, sometimes violently, as they seek to reach a more stable state. This drive towards stability is a key principle behind the formation of compounds. Atoms will lose, gain, or share electrons to achieve a more energetically favorable configuration. This tendency allows complex chemical reactions to occur, reactions that power everything from the combustion of fuels to the metabolism in our cells. Chemical reactions, at their core, are just the rearrangement of atoms. Bonds are broken and formed. Energy is released or absorbed, and yet, through this process, entire systems evolve. Plants grow, stars burn, and thoughts form in human minds. All of it comes down to atoms and the rules they follow. Consider the human brain. It is composed of around 86 billion neurons, each a cell built from molecules, which are built from atoms. When you think, signals pass through your neurons as electrical impulses, which depend on the movement of charged atoms, ions like sodium, potassium, and calcium. The entire experience of consciousness is underpinned by the flow and interaction of atoms. Even memory, emotion, creativity, they all emerge from the dynamic interactions of atoms arranged in complex systems. So when we ask why everything is made of atoms, we are also asking, how is it that such simple particles give rise to such rich phenomena? The answer may lie in scale and organization. An individual atom is simple. A group of atoms, especially when arranged in specific patterns, can perform functions. In large numbers with intricate connections, they form systems capable of learning, adapting, and self-replicating. This is what life is, a dance of atoms structured by the logic of evolution and shaped by the passage of time. Atoms are versatile, stable, and capable of forming vast networks. That's why they were chosen by the unfolding of physical law as the basis for everything. Their properties allow for permanence and change, for order and diversity, for simplicity and complexity. They are the smallest parts of you that still behave like you. Smaller than atoms are subatomic particles, quarks, gluons, leptons. But these do not combine in as many stable or useful ways. Atoms are just small enough to be abundant and just complex enough to build everything. They are the perfect building blocks for a universe that grows, evolves, and dreams. And so we see again and again that the story of atoms is the story of all things. They are the quiet, consistent players in the symphony of matter. They do not demand attention, yet without them, nothing would exist. Not the stars above, not the oceans below, and not the consciousness listening to these words now. Now that we've explored how atoms behave, combine, and contribute to the structure of life and matter, let's turn our attention to how atoms shape the larger universe. Atoms may be tiny, but they are the foundation of every grand cosmic structure. From the grains of sand beneath your feet to entire galaxies spanning millions of light years. To begin, we return to the early universe, just moments after the Big Bang. At that time, there were no atoms, only a hot, dense plasma of fundamental particles. It took roughly 380,000 years of cooling before atoms could form. As the universe expanded and the temperature dropped, protons and electrons finally slowed enough to combine into hydrogen atoms. This event is known as recombination, and it marked the moment when the universe became transparent to light. The first atoms were almost entirely hydrogen, with a trace of helium and an even smaller amount of lithium. These simple atoms floated in darkness until gravity brought them together to form the first stars. Inside those stars, nuclear fusion began to take place. Hydrogen atoms fused into helium, and in more massive stars, helium fused into carbon, oxygen, and heavier elements. Over billions of years, through generations of star birth and death, atoms of increasing complexity were forged. This cosmic recycling process continues today. When massive stars reach the end of their lives, they explode in supernovae, scattering their atoms across space. These remnants mix with clouds of hydrogen gas and dust, eventually collapsing under gravity to form new stars and planets. Every atom in your body, apart from hydrogen, was forged in the core of a star or in the violent aftermath of one. You are quite literally made of stardust. Atoms are also responsible for the structure of planets. Take Earth, for example. Its rocky crust is composed mainly of oxygen, silicon, aluminum, and iron atoms. The oceans are made primarily of hydrogen and oxygen in the form of water molecules. The atmosphere contains nitrogen, oxygen, argon, and trace gases like carbon dioxide. All of these elements are composed of atoms arranged in specific ways that define the planet's chemistry and support life. Even Earth's magnetic field, which protects us from harmful cosmic radiation, arises from the motion of atoms. In the planet's molten iron core, atoms are constantly moving and generating electric currents. These currents create a magnetic field that extends far into space, shielding us from solar wind and charged particles. On a cosmic scale, atoms influence the behavior of galaxies. Though individual atoms are nearly weightless, their sheer number contributes significantly to the mass of stars and gas clouds. In fact, ordinary matter, the kind made of atoms, accounts for about 5% of the total mass energy of the universe. The rest is dark matter and dark energy, which we still do not fully understand. But it is only the atomic matter that forms the structures we can see and study. Within galaxies, atoms combine to form stars, which shine by fusing atoms in their cores. As stars evolve and interact, their gravity shapes the galaxies themselves. The elegant spirals, the glowing cores, the vast interstellar clouds. All of it is made possible by atoms behaving according to known physical laws. But atoms are not just passive components of the cosmos. They respond to forces, exchange energy, and participate in dynamic processes. For example, in the interstellar medium, the vast space between stars, atoms of hydrogen and helium float freely, often ionized by ultraviolet radiation from nearby stars. These atoms can emit or absorb light at specific wavelengths, creating a kind of cosmic fingerprint that astronomers use to study the composition and motion of distant regions. One of the most famous of these fingerprints is the 21-centimeter line, a specific radio wavelength emitted by neutral hydrogen atoms. This signal allows astronomers to map hydrogen gas in galaxies, even those far beyond our own. Without atoms, we would not be able to observe or understand the universe in such detail. Atoms also reveal the temperature, density, and motion of celestial bodies. When we observe the spectrum of a star's light, we can see dark lines, called absorption lines, where specific wavelengths have been absorbed by atoms in the star's atmosphere. Each element has a unique set of lines, allowing scientists to determine what the star is made of, how hot it is, and even how fast it's moving. This technique, known as spectroscopy, has revolutionized our understanding of the cosmos. But beyond the stars, atoms play a key role in the nature of matter itself. Consider the states of matter: solid, liquid, gas, and plasma. These states depend entirely on how atoms are arranged and how they move. In solids, atoms are tightly packed in a fixed arrangement, vibrating in place. In liquids, they are close together but free to move past one another. In gases, they are far apart, moving quickly and colliding only occasionally. Plasma, the fourth state of matter, occurs when atoms are stripped of their electrons, creating a mix of free electrons and nuclei. Plasmas are found in stars, lightning, and certain laboratory conditions. They behave very differently from gases, responding strongly to magnetic and electric fields. Most of the visible matter in the universe is actually in a plasma state. What's remarkable is that all of these states, and all the changes between them, are governed by atomic interactions. When you boil water, freeze it, or melt metal, you are observing atoms shifting between different modes of organization. Even something as simple as a candle flame involves a complex interplay of atoms breaking bonds, forming new ones, and releasing energy in the form of heat and light. That energy, by the way, originates in the bonds between atoms. When atoms come together to form molecules, or when those bonds break apart, energy is either absorbed or released. This is the essence of chemical reactions, and it is the basis for all biological processes. Your body burns glucose molecules by breaking their chemical bonds, releasing energy that powers your cells. Plants, in turn, use sunlight to build those molecules through photosynthesis, capturing energy by forming new atomic arrangements. Even the act of thinking, right now, as you process these words, involves billions of tiny chemical reactions driven by atomic activity. Neurons release neurotransmitters, trigger ion flows, and adjust electrical potentials, all made possible by the movement and behavior of atoms. This raises an important point. Atoms are not static. They vibrate, rotate, and move. They are constantly in motion, even in solid materials. This motion depends on temperature, which itself is a measure of the average kinetic energy of atoms. When you feel warmth, you are sensing atoms moving faster. When something feels cold, its atoms are moving more slowly. In this way, temperature and energy are directly connected to atomic behavior. Even pressure, the force that gases exert on a container, is due to atoms colliding with the walls. The more frequent and energetic the collisions, the higher the pressure. These basic principles explain everything from how lungs inflate to how weather systems form. Atomic motion also gives rise to sound. When you hear a tone or a voice, what you're really detecting is the vibration of air molecules, atoms in motion, moving through the air to your ears. The pitch and volume of sound are determined by how fast and how strongly these atoms vibrate. In essence, sound is an atomic ripple traveling through a medium. So, when we say everything is made of atoms, we don't just mean physical objects. We mean the entire fabric of reality. The light you see, the sound you hear, the warmth you feel, the thoughts you think. All of these experiences are possible because atoms exist, move, and interact. Atoms are not just the scaffolding of matter, they are the carriers of information, the agents of change, and the vehicles of energy. They are the reason why matter can be structured, why life can evolve, and why minds can wonder. And despite their incredible variety and utility, atoms are remarkably few in number when it comes to type. There are only 94 naturally occurring elements on Earth, and a few more that can be created in laboratories. Yet from this small set of atomic types, the universe has built all that we know. This is the brilliance of atomic design, simplicity leading to complexity. The periodic table, often taught as a list of elements, is really a map of atomic behavior. It tells us how atoms will bond, how they'll react, and what kinds of substances they'll form. It shows us trends in size, reactivity, and electronegativity. It's a profound document, a coded guide to the architecture of everything. As we move forward, we'll continue to explore how atoms relate to the deepest questions of reality. For now, it is enough to reflect on this, that atoms are not just the stuff of science. They are the story of existence written in the language of the very small. To understand why everything is made of atoms, it's helpful to step back and look at how we came to know about atoms in the first place. The idea that matter is composed of tiny, indivisible units has existed for millennia. But the journey from ancient philosophy to modern atomic science is a remarkable story of curiosity, observation, and relentless human inquiry. The first recorded atomic theory came from ancient Greece. Around 400 BCE, the philosopher Democritus proposed that all matter was composed of small, indestructible particles he called atomos, meaning uncuttable. He imagined that these particles differed in shape and size, moved through a void, and combined in various ways to form different materials. While this idea was imaginative, it lacked experimental evidence. For centuries, it remained a philosophical curiosity. It wasn't until the 17th and 18th centuries that the scientific revolution provided the tools and mindset needed to investigate the nature of matter systematically. Chemists began to observe patterns in how substances combined. They noticed that elements reacted in fixed ratios by weight, suggesting that something fundamental and consistent was happening at the smallest scales. In the early 1800s, English chemist John Dalton proposed the first scientific atomic theory. He suggested that each chemical element was composed of atoms of a single, unique type, and that chemical reactions were the rearrangement of these atoms. Dalton's theory revived the ancient idea, but now it was grounded in laboratory observations. For the first time, the atom became a testable scientific concept. Over time, as scientists developed better techniques, they uncovered more details. In the late 19th century, experiments with electricity and vacuum tubes led to the discovery of the electron. English physicist J.J. Thomson found that atoms contained tiny, negatively charged particles. This discovery shattered the idea that atoms were indivisible. It suggested that atoms had internal structure. Thomson proposed a model where electrons were embedded within a positively charged pudding, like raisins in a cake. But that idea was soon challenged. In 1909, Ernest Rutherford conducted his famous gold foil experiment. He and his team fired alpha particles, positively charged particles, at a thin sheet of gold foil. To their surprise, most particles passed through, but some bounced back at sharp angles. This indicated that most of an atom is empty space, with a tiny, dense, positively charged nucleus at the center. Rutherford's nuclear model of the atom replaced Thomson's plum pudding idea. It showed that atoms have a compact core made of protons and neutrons, with electrons somehow orbiting around. But this model still had a problem. According to classical physics, orbiting electrons should radiate energy and spiral into the nucleus. Yet atoms are stable. The solution came from Niels Bohr in 1913. He proposed that electrons occupy discrete energy levels, or orbits, and that they could only jump between these levels by absorbing or emitting specific amounts of energy. This quantum leap idea helped explain atomic stability and the spectral lines of hydrogen. Bohr's model marked the beginning of quantum atomic theory. But even Bohr's model had limitations. As more was discovered about electron behavior, it became clear that electrons don't orbit the nucleus like planets around the sun. Instead, they exist in probabilistic clouds, regions of space where they are likely to be found. This idea emerged from the work of scientists like Erwin Schrödinger and Werner Heisenberg in the 1920s. Schrödinger developed a mathematical wave equation to describe how electrons behave, and Heisenberg introduced the uncertainty principle, which states that we cannot know both the exact position and momentum of a particle at the same time. These insights led to the modern quantum mechanical model of the atom. In this model, electrons occupy orbitals, complex shapes defined by probabilities. These orbitals explain why elements bond in specific ways, why molecules have particular geometries, and why materials have different properties. The deeper we've looked, the more layers we've uncovered. In the 20th century, scientists discovered that protons and neutrons themselves are made of even smaller particles, quarks, held together by particles called gluons. This inner world of subatomic particles is described by the Standard Model of particle physics, a framework that explains the behavior of fundamental particles and forces, except for gravity. Yet, even with all this complexity, the atom remains a remarkably stable unit. Its structure allows for both permanence and adaptability. It can remain unchanged for billions of years, or it can join with others to form new substances, new structures, and even new life. The history of atomic discovery is also a testament to human imagination and perseverance. It shows how questions that began as abstract philosophy can lead to concrete discoveries that reshape our understanding of everything. Today, atomic theory forms the foundation of chemistry, physics, biology, and material science. It informs medicine, energy production, technology, and even space exploration. But perhaps what's most inspiring is that atomic theory continues to evolve. With tools like particle accelerators, scanning tunneling microscopes, and quantum computers, scientists are probing deeper into the behavior of atoms and their constituents. We are still discovering new isotopes, observing exotic states of matter, and refining our models of atomic interaction. This ongoing progress reveals a profound truth. Atoms are not just static objects. They are dynamic systems that respond to conditions and interact with their environment. They are active participants in the unfolding drama of the universe. For example, in nuclear physics, we explore how atoms can be split or fused. Nuclear fission involves breaking apart heavy atoms like uranium or plutonium, releasing energy as the nucleus divides. This process powers nuclear reactors and atomic bombs. In contrast, nuclear fusion involves joining light atoms, like hydrogen, to form heavier atoms, releasing even more energy. Fusion is what powers the sun and all stars. and it holds promise as a clean, abundant energy source for the future. Atoms also enable the field of nanotechnology, where scientists manipulate matter at the atomic and molecular scale to build materials and devices with extraordinary properties. Carbon atoms, arranged in different patterns, can form soft graphite, hard diamond, or carbon nanotubes stronger than steel. By precisely positioning atoms, we can engineer materials with specific electrical, optical, or mechanical characteristics. In biology, our understanding of atoms has led to life-saving drugs, advanced medical imaging, and powerful tools like CRISPR, which allow scientists to edit DNA with astonishing precision. All of this is possible because atoms and the molecules they form behave predictably under the right conditions. In astronomy, atomic behavior explains the life cycles of stars, the composition of planets, and the signals we detect from distant galaxies. Without atoms, there would be no light to carry information, no chemistry to sustain life, no gravity-bound structures to populate the cosmos. Even time itself, as we experience it, is measured by the movement of atoms. Atomic clocks use the oscillations of cesium or rubidium atoms to keep time with extraordinary accuracy, accurate to within a fraction of a second over millions of years. These clocks help run GPS satellites, synchronize internet data, and guide spacecraft. All of this brings us back to a simple but profound conclusion. Everything is made of atoms because atoms are the perfect medium for stability, change, structure, and complexity. They are durable enough to persist through cosmic time, yet flexible enough to rearrange and form new things. They bridge the gap between energy and matter, between the chaos of particles and the order of objects. And so we continue to study them, not just to understand what things are made of, but to learn how the universe itself works. Every discovery about atoms opens a new door, reveals a new pattern, and deepens our appreciation for the quiet, invisible architecture of existence. Atoms are not just the smallest recognizable pieces of matter, they are the seeds from which the universe grows. Now that we've traced the evolution of atomic theory and explored the atom's role in shaping matter, we can ask a deeper question. Why is the universe built from atoms and not something else? Why do these tiny structures dominate the physical reality we observe? The answer lies in a delicate balance between the forces of nature, particularly the electromagnetic force and quantum mechanics. Together, they allow atoms to form, to persist, and to combine into everything from stars to cells. Let's begin with the structure of a single atom. At its core, we find a dense nucleus made of protons and neutrons bound tightly together by the strong nuclear force. This is the most powerful force in nature, but it only acts over extremely short distances. Within the nucleus itself, surrounding this nucleus is a cloud of electrons. These electrons are held in place by the electromagnetic force, which attracts negatively charged electrons to the positively charged protons in the nucleus. But electrons don't simply spiral into the nucleus. They exist in quantized energy levels, specific states where they can remain stable, thanks to the principles of quantum mechanics. In classical physics, an object could exist at any energy level, but quantum systems are different. Electrons can only occupy discrete energy levels. They can jump between them, but only by absorbing or releasing a precise amount of energy. This creates the beautiful and predictable structure of the periodic table, each element having a unique atomic number and arrangement of electrons. The structure of the atom, the balance between the attractive electromagnetic force and the principles of quantum behavior, makes atoms incredibly stable. They don't collapse in on themselves, nor do their components fly apart. This stability is crucial. Without it, matter could not persist. But stability isn't the whole story. Atoms are also versatile. Electrons can be shared or transferred between atoms, forming chemical bonds. These bonds come in different types: covalent, ionic, metallic, each with its own behavior and function. Through bonding, atoms assemble into molecules, and molecules into materials. This ability to combine, reconfigure, and react is the basis of all chemistry. It's also the basis of life. Carbon, for example, has 4 electrons available for bonding, allowing it to form an astonishing variety of structures: chains, rings, lattices. It can bond with hydrogen, oxygen, nitrogen, and countless other elements to create the complex molecules that form proteins, DNA, and living cells. Without atoms and their particular behaviors, life would be impossible. Atoms also provide the scaffolding for phase changes, the transformations between solid, liquid, gas, and plasma. These changes are driven by energy, which affects how atoms move and interact. In solids, atoms are tightly bound in a fixed arrangement. In liquids, they slide past one another. In gases, they fly freely. In plasmas, electrons are stripped away, creating an ionized state seen in stars and lightning. These transitions are essential to the natural world: water cycling through evaporation and condensation, lava cooling into rock, ice melting in the spring. Each transformation is a dance of atoms responding to energy. And speaking of energy, atoms are also the gatekeepers of light. When an atom's electron absorbs energy, it can jump to a higher energy level. When it falls back, it releases that energy as a photon, a particle of light. This process is how stars shine, how neon signs glow, and how our eyes perceive color. Each element emits and absorbs light at specific wavelengths. This gives every atom a spectral fingerprint, a unique signature that allows scientists to identify elements in distant stars, analyze chemical compositions, and study the early universe. Even more astonishing is how atomic structure gives rise to the materials we use every day. The hardness of diamond, the conductivity of copper, the flexibility of rubber, all arise from how atoms are arranged and bonded. Engineers manipulate atoms to create new materials: superconductors, solar panels, semiconductors, and nanomaterials with properties no natural material has. Atoms can also behave in collective, cooperative ways. In quantum materials, electrons synchronize in strange patterns, giving rise to phenomena like superconductivity, where electricity flows without resistance, or Bose-Einstein condensates, where atoms behave as one quantum entity. These behaviors defy our everyday experience, but they're deeply rooted in atomic structure. Even our technology depends on our understanding of atoms. Transistors, the building blocks of computers, work by controlling the movement of electrons through materials. Lasers rely on controlled photon emission from atoms. Atomic clocks define the second. MRI scanners map the spin of atomic nuclei in the body. But perhaps one of the most mysterious and powerful aspects of atoms is their role in nuclear energy. As we mentioned in Part 5, the nucleus contains nearly all of the atom's mass, and it's held together by the strong force. But if that balance is disrupted by splitting a nucleus, fission, or fusing two together, fusion, an enormous amount of energy is released. This is the basis for nuclear power plants, and for the energy that fuels the sun. In fusion, light elements like hydrogen combine to form helium, releasing energy. In fission, heavy elements like uranium are split into smaller nuclei, also releasing energy. Both processes convert a small amount of mass into energy, as described by Einstein's famous equation, E is in mc2. This means that atoms are not just passive structures, they are reservoirs of energy, capable of changing form and releasing incredible power under the right conditions. This duality, structure and energy, makes atoms both stable and dynamic, enduring and transformative. Atoms also help us understand time itself. As we mentioned earlier, atomic clocks use the vibrations of atoms, especially cesium and rubidium, to measure time with extraordinary accuracy. These clocks are so precise they only lose 1 second every millions of years. They're used in GPS systems, in global communications, and in studying fundamental physics. In cosmology, we use atomic data to trace the history of the universe. The light from distant galaxies is stretched by the expansion of space, and by analyzing the atomic spectral lines in this light, we can learn how fast the universe is expanding, how old it is, and what it's made of. In short, atoms are not just building blocks. They are narrators. They carry information, they record change, they echo the forces that shape the universe. Every grain of sand, every drop of water, every cell in your body is made of atoms that have existed for billions of years. These atoms were forged in the hearts of stars, scattered across the cosmos in supernova explosions, gathered into planets, and eventually into living beings. You are, quite literally, made of stardust, assembled from ancient atoms that once burned in stellar cores. Atoms persist through time. When a living thing dies, its atoms return to the environment, recycled again and again through nature. The calcium in your bones, the iron in your blood, the oxygen you breathe, all have been part of countless systems before you. So when we ask why everything is made of atoms, we are really asking why the universe chose such an elegant, enduring, and expressive medium for its creation. Atoms are nature's quiet, tireless artisans. They hold memory, structure, potential. They are everywhere and everything. They shape the visible world and the invisible. And though they are unimaginably small, their impact is cosmic in scale. When we think about atoms, we often imagine them individually, tiny building blocks invisible to the naked eye. But most of the universe doesn't exist as isolated atoms. Instead, atoms work together in vast numbers, billions upon billions, forming the matter we interact with every day. In this part, we'll explore what happens when atoms gather, how they behave as groups, and how their collective activity gives rise to the familiar laws of thermodynamics, temperature, and pressure, the fundamental rules that govern matter in bulk. Let's begin with the concept of temperature. Temperature is not a property of a single atom. Instead, it's a measure of the average kinetic energy, the energy of motion, of all the atoms or molecules in a substance. When you heat something up, you're increasing the motion of its atoms. They vibrate more rapidly in a solid, flow more freely in a liquid, and move chaotically in a gas. Even the coldest materials have some atomic motion. In fact, the coldest possible temperature, absolute zero, is defined as the point at which all atomic motion stops. That's 0 kelvins, or 273 degrees Celsius. But even at temperatures close to absolute zero, quantum effects still allow for strange, subtle behavior. In a gas, atoms zip around freely, bouncing off each other and the walls of their container. Each collision transfers energy. The pressure a gas exerts on its container is just the result of countless atomic impacts over time. So even something as familiar as air pressure is really a story of atoms in constant motion, pushing and colliding invisibly. If we increase the temperature of a gas, its atoms move faster, hit harder, and the pressure increases. This relationship between pressure, volume, and temperature is described by the ideal gas law, a simple equation that links atomic motion to macroscopic behavior. But gases aren't the only state of matter atoms can occupy. In solids, atoms don't fly around freely. Instead, they vibrate in place, held in a rigid lattice by strong chemical bonds. The arrangement of atoms determines whether a solid is hard, soft, brittle, or flexible. Crystals, like salt or diamonds, have atoms arranged in precise, repeating patterns. This regularity gives them their characteristic shapes and properties. On the other hand, materials like glass have atoms arranged randomly, making them amorphous solids with very different behaviors. In liquids, atoms are still close together, but they're not locked in place. They slide and flow around each other, constantly forming and breaking temporary bonds. This fluidity is what allows water to pour, waves to ripple, and currents to flow. So how do these atomic motions give rise to heat and energy? When atoms move, they carry energy, thermal energy. When energy flows from one region to another due to a difference in temperature, we call it heat. This can happen in three main ways: conduction, convection, and radiation. In conduction, atoms pass energy directly to their neighbors through collisions. Metals are excellent conductors because their electrons are free to move and transfer energy quickly. In convection, atoms move in bulk. Warm fluid rises, cooler fluid sinks, carrying heat with them. This happens in boiling water, atmospheric circulation, and even inside stars. In radiation, atoms release electromagnetic energy, often as infrared light, which travels through space and is absorbed by other atoms. This is how the sun warms Earth across the vacuum of space. At the heart of all these processes are atoms in motion. Their interactions and exchanges of energy create the behaviors we associate with heat, cold, flow, and resistance. But atomic behavior goes even deeper. Let's look at phase transitions, the moments when matter changes from one state to another. When you boil water, you're not just adding heat. You're supplying enough energy for water molecules to overcome the attractive forces between them and escape into the gas phase. The same happens when ice melts. Heat breaks the rigid structure of solid water, allowing the atoms to move more freely. During these transitions, something amazing happens. The temperature can remain constant even as heat is added. That's because the energy is being used to break bonds, not increase motion. This is called latent heat, and it's one of the fascinating consequences of atomic interactions. But atoms don't always behave predictably. At very low temperatures, or in extreme conditions, atoms can do strange things that defy our classical understanding. One example is superfluidity, where a liquid can flow without any resistance. Another is Bose-Einstein condensation, where atoms lose their individual identity and act as a single quantum wave. These behaviors reveal the quantum side of atomic physics, showing that even when atoms act collectively, their strange subatomic rules still apply. Now let's talk about entropy, one of the most intriguing and misunderstood concepts in science. Entropy is a measure of disorder, or more precisely, the number of possible ways atoms in a system can be arranged. A perfectly ordered crystal has low entropy. A cloud of gas has high entropy because its atoms can be in many configurations. In thermodynamics, entropy tends to increase. This is known as the second law of thermodynamics, one of the most important rules in physics. It says that over time, energy spreads out, disorder increases, and systems tend toward equilibrium. This is why hot coffee cools down in a room, why a broken glass doesn't reassemble, and why the universe itself is slowly moving toward a state of maximum entropy. But entropy isn't just decay or chaos, it's the engine of change. Life itself is a low entropy phenomenon that survives by taking in energy from the environment, like sunlight, and releasing waste heat. The complexity of living systems emerges from countless atomic interactions operating far from equilibrium. Even time seems to flow in one direction because of entropy. As atoms move from ordered to disordered states, we experience the arrow of time, past to future. Without atomic motion and energy transfer, time would have no meaning. Atoms also explain buoyancy, sound, elasticity, and even the feel of textures. The softness of a pillow, the crunch of leaves, the vibration of a guitar string, all come from how atoms are arranged and how they respond to force. In the realm of biology, atomic behavior is even more profound. Proteins fold into precise shapes. DNA coils and uncoils, neurons fire, all based on the subtle movements and charges of atoms in water, salt, and carbon-based molecules. Atoms even influence color, taste, and smell. The pigments in your eyes, the receptors on your tongue, the molecules in a flower's scent, all are atomic arrangements interacting with your body in incredibly detailed ways. So when we say everything is made of atoms, we don't just mean that atoms are the ingredients. We mean that their collective behavior gives rise to the very experience of reality. They are not passive. They dance, vibrate, collide, transform. They follow laws and yet surprise us. And when they work together, they create everything from the breath in your lungs to the glow of distant galaxies. Atoms are tiny beyond comprehension, yet their influence stretches across the vastness of the cosmos. In this part, we'll explore how atoms shape the universe on a grand scale, from the fiery hearts of stars to the spiral arms of galaxies, and even to the hidden matter that seems to lie beyond the reach of our senses. Let's begin with the stars. Every star you see in the night sky is a giant ball of atoms, mostly hydrogen, being pulled inward by gravity and pushed outward by fusion. At the core of a star, temperatures and pressures become so intense that atoms are stripped of their electrons, forming a state of matter called plasma. In this extreme environment, nuclear fusion occurs. Hydrogen nuclei, protons, smash together and fuse to form helium. This process releases enormous amounts of energy, which radiates outward and gives stars their light. Fusion is the reason stars shine, and it's entirely an atomic process. But it doesn't stop with hydrogen. In more massive stars, the fusion continues, so helium becomes carbon, carbon becomes oxygen, and so on, building heavier and heavier elements all the way up to iron. However, fusing iron doesn't produce energy. Instead, it consumes it. So when a star builds up too much iron in its core, it reaches a tipping point. Gravity takes over, the core collapses, and the star explodes in a supernova, one of the most violent events in the universe. In that moment, even heavier elements are created: gold, uranium, platinum, atoms that couldn't be made in normal stars. These elements are flung out into space, enriching the galaxy and seeding future generations of stars and planets. The iron in your blood, the calcium in your bones, the oxygen you breathe, they were all forged in the heart of a dying star. So when we say you are made of stardust, it's not a metaphor. It's atomic truth. These atoms then gather into clouds of gas and dust, nebulae, where gravity begins its slow, inevitable work again. Clumps of matter form, spin, and collapse, creating new stars, new solar systems, and eventually, new worlds. Let's zoom out to an even grander scale, galaxies. Galaxies are vast islands of stars, gas, and dust, held together by gravity. The Milky Way, our home galaxy, contains over 100 billion stars, each made of countless atoms. Galaxies come in many shapes: spiral, elliptical, irregular, and they often collide and merge, creating bursts of star formation and reshaping the structure of the cosmos. But something strange happens when we study the motions of galaxies. When astronomers measured how stars move within galaxies, they found that the stars are orbiting much faster than they should be, based on the visible matter alone. This suggests there's more mass than we can see, something exerting gravitational pull, but invisible to our instruments. We call it dark matter. Dark matter does not emit light, does not absorb it, and does not interact with regular atoms except through gravity. It makes up about 85% of the matter in the universe, and yet we still don't know exactly what it's made of. It may be composed of exotic particles, perhaps WIMPs, weakly interacting massive particles, or axions, that don't form atoms like ordinary matter. Or it could be something even stranger, perhaps a new kind of atom-like structure we haven't yet imagined. Whatever it is, dark matter shapes the universe. It forms vast cosmic scaffolding around which galaxies cluster. Without it, the universe, as we know it, could not have formed. So while atoms are the stars of the show when it comes to ordinary matter, they may only be a small piece of a much larger puzzle. And beyond dark matter, there's also dark energy, an even more mysterious force that seems to be driving the expansion of the universe faster and faster. While atoms and gravity pull things together, dark energy pushes them apart. It's hard to imagine that the tiniest building blocks of matter, atoms, play such a pivotal role in this cosmic drama. But they do. Their behavior determines how stars burn, how galaxies form, and how the visible universe evolves over time. Even cosmic background radiation, the faint afterglow of the Big Bang, tells the story of atoms. In the early universe, when everything was hot and dense, atoms couldn't form. It wasn't until about 380,000 years after the Big Bang that the universe cooled enough for electrons and protons to combine and create neutral atoms. This era, known as recombination, allowed light to travel freely through space for the first time. That light still reaches us today as the cosmic microwave background, a snapshot of the universe when it was just a baby. By studying tiny variations in that background, scientists can map the distribution of atoms across the cosmos and understand how structures like galaxies and clusters came to be. So from the tiniest atoms to the grandest galaxy clusters, everything is connected. The universe is not just a place filled with atoms, it's a place shaped by them, and it continues to evolve. Stars live and die, galaxies collide and grow, and atoms are recycled again and again across cosmic time. In every star that burns, every planet that forms, and every breath you take, the story of atoms continues. Atoms are everywhere. But for most of human history, we didn't know they existed. The idea that matter is made of indivisible particles goes back over 2,000 years. In ancient Greece, philosophers like Democritus proposed that if you keep cutting a substance in half, eventually you'll reach a point where it can't be divided anymore. He called these ultimate particles atomos, meaning uncuttable. It was a bold idea, but it wasn't based on experiments. For centuries, it remained just that, an idea. The scientific understanding of atoms didn't begin to take shape until the 1800s, when John Dalton proposed the first modern atomic theory. Dalton suggested that all matter is made of tiny, indivisible atoms. Each element has its own unique type, and chemical reactions are rearrangements of these atoms. Dalton's model was simple and solid, atoms as hard, indivisible spheres. But as science advanced, cracks began to appear in this picture. In 1897, J.J. Thomson discovered the electron, a tiny negatively charged particle inside the atom. This meant atoms weren't indivisible after all. They had internal structure. Thomson proposed a new model, often called the plum pudding model, where electrons floated in a positively charged soup, like raisins in a pudding. But that too would soon be replaced. In 1909, Ernest Rutherford conducted a famous experiment in which he fired alpha particles at thin gold foil. Most of the particles passed through, but a few bounced back. This surprised everyone and led Rutherford to a revolutionary conclusion. Atoms are mostly empty space. At their center is a small, dense, positively charged nucleus, and the electrons orbit around it. This nuclear model changed everything. But there was still a problem. According to classical physics, electrons orbiting a nucleus should radiate energy and spiral inward, causing the atom to collapse. That clearly wasn't happening. Atoms were stable. The answer came from Niels Bohr, who introduced quantum ideas into atomic structure. In his model, electrons could only occupy specific energy levels or orbits around the nucleus. They didn't lose energy while in these orbits. They could jump from one orbit to another, absorbing or emitting energy in the form of light. Bohr's model explained the behavior of hydrogen atoms beautifully, but couldn't handle more complex atoms. That's when quantum mechanics entered the scene. In the 1920s, physicists like Erwin Schrödinger, Werner Heisenberg, and Paul Dirac developed a new way to describe the atom, one based on probability, not certainty. Electrons weren't tiny balls following precise orbits. They were described by wave functions, mathematical expressions that showed the probability of finding an electron in a certain region of space. This led to the concept of electron clouds, regions around the nucleus where electrons are likely to be found. The exact position of an electron couldn't be known, only the likelihood of where it might be. This uncertainty wasn't just a limitation of our tools, it was a fundamental feature of reality itself. Heisenberg's uncertainty principle showed that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. Atoms were no longer just particles, they were both waves and particles, depending on how you observed them. This dual nature lies at the heart of quantum mechanics, and it's how atoms truly behave. Further discoveries revealed the structure of the nucleus itself. The nucleus contains protons, which are positively charged, and neutrons, which have no charge. These particles are made of even smaller ones, quarks, held together by the strong nuclear force, one of the four fundamental forces of nature. The more we learned, the more intricate atoms became. They are not solid spheres or simple building blocks. They are complex systems governed by strange quantum rules. Our growing understanding of atoms revolutionized science and transformed the world. In the early 20th century, quantum mechanics and atomic theory led to breakthroughs in electronics, chemistry, and energy. We built transistors, which led to computers. We harnessed nuclear fission, leading to both nuclear power and nuclear weapons. We learned to manipulate atoms and molecules, creating new materials, medicines, and technologies. The periodic table, once just a clever arrangement of elements, became a roadmap for atomic structure. Each element's behavior, its reactivity, its bonds, its place in the universe, could now be understood by the arrangement of its electrons. Even the color of a flame or the spectrum of starlight could be traced back to electron transitions, atoms absorbing and emitting light at precise frequencies. Today, we continue to push atomic science even further. We smash particles together in giant accelerators to understand what lies beyond the atom. We cool atoms to near absolute zero to explore strange quantum states like Bose-Einstein condensates. We use scanning tunneling microscopes to move individual atoms into place, creating structures one atom at a time. In fields like quantum computing, atoms and their energy states are being used to create entirely new forms of information processing. Machines that might one day solve problems classical computers never could. Our journey through atomic understanding has changed how we see the world and ourselves. We've gone from philosophical guesswork to precise, predictive science. From thinking of atoms as uncuttable marbles to embracing their quantum weirdness. From wondering what things are made of to manipulating the building blocks of matter itself. Atoms are not just small, they are the interface between what we can see and what we cannot. They are the keys to chemistry, to physics, to life. Atoms, the tiny building blocks that shape the entire universe. After journeying through their structure, their behavior, and their history, we return to a fundamental question. Why is everything made of atoms? Why not something else? Why not some continuous uniform matter? Why not points of light or waves alone? The answer lies in the remarkable balance that atoms strike. They are the perfect intersection of stability and change, of simplicity and complexity. Atoms are stable, their structure, nucleus and electrons, allows them to persist across time and space. The electromagnetic force binds electrons to nuclei in predictable patterns. The strong nuclear force keeps protons and neutrons locked together at the heart of each atom. These forces are just strong enough to form structure, yet balanced enough to allow interaction. Without this stability, the universe would be a formless soup of energy, but with it, matter can persist. Atoms can form, and from atoms, everything else. Yet atoms are not too stable. They are dynamic, they interact, they bond, they exchange energy. The outer electrons of atoms, especially those in the valence shell, are ready to form links with other atoms. These connections are the roots of chemistry, and through chemistry, the emergence of molecules, of reactions, of life. This balance between being bound and being free makes atoms the perfect foundation for a dynamic universe. Atoms are also modular. You don't need billions of different types of building blocks. With just around 100 elements, atoms can assemble into nearly limitless forms. Carbon atoms, arranged one way, make graphite. Arranged another, they form diamonds. Combined with hydrogen, oxygen, and nitrogen, they build DNA, proteins, and the cells that make up life itself. The same atoms that formed in the early universe are still here, recycled across stars, planets, oceans, and living beings. Atoms give the universe structure, but also flexibility. They are small enough to allow fine-grained complexity, but large enough to organize into patterns. Their scale lets them form lattices in crystals, membranes in cells, circuits in computers. Without atoms, there would be no galaxies, no stars, no Earth, no air to breathe or water to drink, no thoughts or emotions, no you and no me. Atoms are not just useful, they are necessary, an inevitable outcome of the rules that govern our universe. Let's take a step even further back. Why do atoms exist in the first place? The answer traces back to the early universe. After the Big Bang, the cosmos was a sea of energy. As it expanded and cooled, this energy condensed into matter. First came quarks and gluons, then protons and neutrons. And then, about 380,000 years after the Big Bang, the universe cooled enough for electrons to orbit nuclei. Atoms were born. And once atoms existed, everything else became possible. Stars ignited, fusing simple atoms into heavier ones. Supernovae scattered these atoms into space, seeding galaxies with carbon, nitrogen, oxygen. These atoms collected into clouds, planets, oceans, and eventually living organisms. Atoms formed the canvas for evolution, biology, and consciousness. It's tempting to think of atoms as tiny, lifeless particles, but they are active participants in the story of the universe. Atoms store energy. They absorb light. They emit photons. They vibrate. They bond. They shape the texture of reality itself. Even the colours we see, the sounds we hear, and the scents we perceive all depend on atomic behaviour. Molecules shaped by atoms interact with our senses, sending signals to our brains. Our every sensation, our every experience, flows through atomic interactions. Atoms are not just what things are made of, they are how things are. They set the rules, they provide the options, and they support the unfolding complexity that makes the universe beautiful and strange. Why is everything made of atoms? Because the fundamental forces of the universe allow it. Because atoms balance unity and diversity. Because they can combine, transform, and evolve. Because they work. And perhaps most mysteriously, because atoms can give rise to self-awareness. We are made of atoms, yet we can contemplate atoms. The universe has become aware of itself through us, and that perhaps is the most extraordinary fact of all.
So tonight, as you drift off to sleep, remember this.
Everything you see, touch, feel, and are is made of atoms, forged in stars, bound by invisible forces, moving in quiet, endless patterns. You are part of this grand atomic tapestry, woven across time and space. Sleep well and let the atoms do their work.